Hello, everyone. I'm Łukasz, and I would like today to talk about the methods of using reinforcement learning for online sequence transformation. Okay, so we have the agenda for my presentation. First, I will do a short overview of the related work to our method. Then I will define the problem that we wish to solve. Then I will present the method and architecture of our solution. After which I will discuss and present the experiments that we conducted from our method and similar to it, and then we'll discuss the results we obtained. Uh, so, when it comes to related work, we have three main areas. The first one is neural machine translation, which processes input sequences and tries to translate them to output sequences. In this area, we have mostly encoder-decoder architectures, sometimes with attention, at which transformers are state of the art right now. This method requires the whole input to be processed by the architecture in order to produce output. The second area that we focus on reinforcement learning, especially the partially observable macro decision process, in which we don't have the access to the whole state of the environment. We only have some limited observations of on which basis we have to do out those actions. And the third area that we focus on is the simultaneous machine translation. The difference between SNP and NNP is that the SNP produces output during processing input, so that's it's more parallel. Many of these methods are reinforcement learning based, which like connects the neural machine translation and reinforcement learning. In this, the most common is the two-action framework, in which the agent has two actions: read for reading the next token from the input sequence and write to write the new token to the output sequence. There are also some methods that enhance the NNP methods to become SNP, but today we'll focus on this two-action framework. So the problem that we wish to solve is as follows. The first we have the input, which is some sequence of tokens, for example, a sentence in one language. The output, the sequence of tokens that corresponds to this input sequence, for example, the sentence in another language. And we have the interpreter agent that produces another sequence of tokens that should be as similar to the second sequence as possible. So the sequence that has to minimize this quality index defined by J on the slide, which is a sum of losses from tokens in Y and Z sequences. This loss penalizes mistranslation, so the errors in translation, like for example, we have the wrong word or we use the wrong word in some context. Very important assumption is that the agent operates online, so it reads input and produces output at the same time. So it's not NNP, it's SNP. We also have some special tokens in our sequences. Null is for the unknown token. Path is for making the sequences equal in length. So it's easier for processing, for batch processing, and we have also the EOS token, which is for end of sentence. So our method is an agent that is learned with reinforcement and can take two actions, which I mentioned earlier. The first one is read, so get next token from the input sequence and use it in your processing, or write, which is write the next token to the output that an agent is processing. The agent, during its operation, receives rewards, and these rewards are given for writing output token. This reward is equal to the negative mistranslation loss, and the agent also gets reward for taking read action after reading the full input, after which he is penalized for doing so because he can't read anymore. So this is a very big negative reward. The agent length is policy which is to maximize sum of discounted rewards, so that this the best when the policy when the sum is maximized, the produced translations of equal length as the target and has the same tokens. The observations that the agent gets are last read token from the input and last written token to the output. So this is the partially observable environment because we do not have access to all tokens that we read before or tokens that we've written before. And the episode of the agent is a translation processing of a single sequence. So here we'll talk about our architecture, and the policy of our architecture encompasses a recurrent neural network, which is useful for partially observable Markov decision processes. So the input that our network gets is the last token read from input and the last token written to output. They are set to unknown when we use the write action. When we use the write, the last token read is set to null when we use the write action, and the last token written is set to null when we use the read action, so that the information that agent gets is actually only the part of input or part of output. We also utilize teacher forcing in a way that instead of using tokens we produced as last token written, we use the tokens from the target output, which helps the agent learn. This input on the image on the right are represented by X, Y, and ZJ. The output that the policy produces is the potential output token that we may wish to save to the output sequence, and the return estimates for actions that we want to take. This is marked as NTR and NTP, which is the potential token output token, and NTR and NTW are return estimates for actions that we wish to take in the next step. At the bottom, we can see the definition of PT value, which is the value that the return estimates are going to be pushed to, so that for example, if we take the action read and we have the finished sentence, we get the minus m plus gamma max q from the next time step, so that we penalize this action because we've read after reading the whole input. But still we may want to write something. For if we read and we haven't finished reading the input sentence, then we just take the maximum from the next time step. If we write and we are not at the end length of the target sequence, we get the minus mistranslation loss and the discounted value of the next action. And if we are writing last token, we just get the mistranslation loss. And the one thing that's important here is that the mistranslation and return estimate losses that we calculate are weighted because they are qualitatively different losses. They may have different scale, different values. So we have to scale them so that their input to the aggregate loss is equal. And the thing we are minimizing is this aggregated loss of potential output token and return estimate. Okay, so for the experiments, we did experiments on machine translation text. We used AAIA'22, which is the community-created data set of sentences in many languages. We did 5 experiments on that, to which we used our own code. And we also conducted experiments for AAIA'22 2014 machine translation benchmark. For this, we use the Parsec library. We tested 3 architectures, the standard encoder-decoder architecture with attention, and we based this architecture on GRU neural network cells. We also tested the basic transformer in experiment on AAIA'22. coded both encoder, decoder, and transformer. In IWSLT, we use the transformers and encoder decoders provided in the library and with optimized settings. And we also tested our method RLST, to which we optimized settings in both scenarios. We report below values on test sets from the data sets we use, and the epoch on which the architectures are tested is chosen on the base of validation below, and which is the epoch on which this value was the highest. As mistranslation loss, we use the cross entropy, and for the return estimate loss for our agent, we use mean square error. Okay, so here are the results that we obtained, and one more thing to add is that for Tatueba dataset, we have two test sets defined. The first one is the regular, let's call it regular test set, and there we have source sentences that are no longer than 20 tokens, and we also took the long test splits where source sentences were longer than 22 tokens. This was done to check how the agents and tested architectures behave when they have to process longer inputs. And bolded are the best results for the language per tested. So, for example, for Tatueba Espanol English, the best below value on regular test set was encoder decoder based on GRU, but on long tests our architecture was the best. Okay, so to discuss these results, so we have similar results on all architectures on regular Tatueba set. So as we can see, every architecture was able to get good results on this data set, and they are mostly similar on regular test sets. But on long test sets, in 4 out of 5 instances of Tatueba, our architecture got the best results, which means that our agent was able to preserve the context of longer sentences that it was processing. We think that the more context that was in these sentences allowed our agent to better use its limited memory capacity to memorize the state of the environment. On the IWSLT benchmark, the transformer got the best results, beating our method and the encoder-decoder architecture. However, our method got similar results to encoder-decoder. And we think that because this dataset got a bit shorter sentences and our agent wasn't able to find this context so easily as in long datasets on long sentences in Tatueba. So we think that our agent is well adapted to processing sequential data, especially when it's very long or we need online processing without the limit of length, because it's able to save the state of the environment with limited memory and use it for further translation. And that's everything I wanted to share with you. Thank you very much.
Hi, how are you? Yes, thank you for your interesting talk. Actually, this is David. I'm from Singapore. So just 2 questions. First, your corpus is English only, or I saw you're from Poland, or is the Poland corpus? Your sentence, your language is English, right? English, or is Poland language, or?
That was the question.
Yeah, you.
So we have 5 language pairs for the Tatueba data set, and this is Spanish to English, French to English, English to Spanish, English to Russian, and English to German. And for the second data set, we have English, German, and German English language pairs.
Okay, all right. My second is actually we use a lot of statistic, the machine learning on the machine translation. Did you have ever tried some other? Because I saw you have benchmark, right? So what method what algorithm you are trying to compare or beat? Yeah, okay.
It's hard to hear this question.
Oh yeah. I mean, actually, we used to a lot of statistic machine translation, the models or algorithms. So, what kind of you try to compare your algorithm with other tools or yeah?
Okay, so we are comparing with the standard neural machine translation method, not simultaneous machine translation method. We intend to test against other simultaneous machine translation methods in the future, but we compare to the neural machine translation methods mostly used right now. So the transformer architecture, that is one of the best, but we use the base transformer, not it's one of its modifications, and the encoder-decoder architecture, which was used before that.
Actually, roughly, you mainly use a neural network. Yeah. Okay. Okay. All right. It's okay. Yeah. Sounds good. Yeah.
Yeah.
Any further questions, comments? I just want to ask one question because I seem to have missed that bit if it was before. Those two benchmark data sets, what is their size and how they relate to the actual task of translating between, let's say, English and French? So, how much of a language corpus do they cover?
Okay, so I will start with Tatueba data sets. Actually, their size varies between language pairs. I think the biggest one was Spanish to English, but the Tatueba data sets are easier because they are community created, and actually there's a lot of translations that repeat themselves. So actually, architectures got easier time learning them. IWSLT is smaller than many Tatueba datasets. I think this is tens of thousands of sentences, but this is the benchmark that was defined as a competition in 2014. So the translations are a bit harder, which we can see on these results where Tatueba sets have a lot higher BLEU values and IWSLT is actually a lot lower.
Yeah, and do we know how, let's say, how representative are those data sets? So if I take those, this or that benchmark and teach my model to do the translation, what is the chance it will behave properly in the real life scenario?
So I think that Tatueba datasets may have here a better chance because they have more like common language, more informal sentences that we use every day, while the benchmark is composed from some official sources. I don't remember exactly what they are right now, but for example, there may be some news coverages translated, or I don't know if this benchmark has these sentences, but one of them has European Parliament debates translated from one language to another. So these are very official sources.
Okay, thank you very much. Then